Hello, everybody. Today's topic for physics is the dispersion of light. And dispersion is what causes rainbows. But in order to understand them, we have to go back and get some background information on light first. So let's do that. The first thing you should know is that light is a form of energy, and we call it electromagnetic radiation. Now, so that's the first thing to understand, that light is a form of energy. Second, light behaves as a wave. In other words, it has a frequency and a wavelength, which you're already familiar with those concepts from earlier in the year. But you know from the wave equation, which is frequency times wavelength equals speed, and also from the fact that the speed of light is constant in a given medium, this means that frequency and wavelength of light are going to be inversely related to each other. Now, the visible light that we can see occurs within a defined set of frequencies or wavelengths. Doesn't matter which one you define because they're inversely proportional to each other. But it's part of all electromagnetic radiation. And so we envision all electromagnetic radiation is occurring on a spectrum of all combinations of frequency and wavelength. And visible light is just a small portion of that spectrum. You can see here that the other portions of the spectrum have different names. For example, long wavelength electromagnetic radiation is referred to as radio waves. And as the waves get slightly shorter, we call them microwaves, which are used in cooking, and they're also used in telecommunications. And as they get still shorter, we talk about infrared waves, which we often associate with heat. Then we have the visible spectrum. And then as we get shorter wavelengths in the visible spectrum, we get ultraviolet light, and that's what's responsible for sunburn when you get sunburn. And then still shorter are referred to X-rays, and they're used as in medical technology to view your bones and other parts of your anatomy. And then as we get still shorter, we get to gamma rays, which occur in some radioactive elements on Earth and in some stars in space. So let's take a slightly deeper dive into this. Radio waves, their wavelength is about 1 kilometer long, the size of the very tallest buildings. Microwaves are about 1 centimeter long, 10 to the minus 2 meters, right? And by the time you get down to gamma rays, they're about 10 to the minus 12 meters long, which means they're about the size of an atomic nucleus. So this is the entire spectrum of electromagnetic radiation, of which only a small portion is visible light. Now, if we take white light and shine it through a prism, we can break it into a rainbow, into its rainbow colors. And in other words, white light is really composed of all the different colors of the rainbow. The same thing happens in the upper atmosphere when there are water droplets dispersed, and each of those water droplets acts as a little tiny prism and sends a rainbow of light to your eye. So in other words, as I said already, white light is a combination of all colors, all frequencies in the visible spectrum. And sunlight is white light. So in physics, we use only 6 colors, Roy, G, B. We don't use indigo. And I did a little bit of a deep dive into this, and it's a little bit controversial. But the reason that indigo is omitted is because it would have the shortest quantity of frequencies associated with it, and so it gets lumped into blue. But when Isaac Newton first noted this phenomenon, the blue he saw was the color of sky blue, and the indigo he saw was the color of dark blue jeans, and violet is violet. So visible red light starts at a frequency about 4.55 times 10 to the 14 hertz. That's 4.55 times 10 to the 14th waves per second. And violet light, the last visible violet light you can see, is about 7.32 times 10 to the 14 hertz. So you can see that it's all within the 10 to the 14 hertz area, but so it doesn't even vary by an order of magnitude, the frequency of the lights we can see. And similarly, here are the inversely proportional wavelengths. The low frequency red light has the highest wavelength at 660 nanometers, that's 10 to the minus 9 meters, and the violet light has the smallest wavelength at 410 nanometers. Now, here's the idea of what goes on in a prism. The different colors of light bend by different amounts when they go through a border into a new material. The only exception to that is when light goes from vacuum to air. There is no bending of the different colors in air. They all have the same index of refraction in air, and in all other media they have different indices of refraction. And what this means is that n equals 1 for air for all colors. All right. So we can fill in tables like this where you can see here is our electromagnetic spectrum. Here is the index of refraction for each color in air, and it's always 1. But now look at diamond. Red has an index refraction of 2.410 and violet of 2.458. And now here you can start to guess at the reason why we insisted you put down 4 numbers for the index of refraction. Some of these differences are going to be so small between the index of refraction of the various colors that we're going to need 4 places to see the difference and to use it in calculations. So let's now take out your packet and do problem 5. And so here it is. Sunlight travels through air and enters crown glass at an angle of 38 degrees. Solve for the index of refraction in crown glass for orange light if the angle of refraction is 23.86. So our boundary is between air and crown glass, and what you should first do is write down the knowns and the unknowns. Well, hopefully you wrote the following, that the n of air is 1, the n of crown glass is the unknown, and the angle of incidence is 38 degrees and the angle of refraction is 23.86 degrees. Now, what equation are you going to use to calculate the n of crown glass? Well, hopefully you said Snell's law and you wrote it down and it looked like this. And now what you're going to do is you are going to do the algebra and get n of crown glass by itself, right? That's an important next step. So here's n of crown glass by itself. N of crown glass equals n of air times sine theta air divided by the sine theta of crown glass. And now you will do the substitution, okay? And there's your answer. When you put all the numbers in, you get 1.522. I can't emphasize this enough. I have taught 9th graders physics for over 20 years. It is really important you do the algebra on the variables first and then substitute in. Also, if you want to simplify this, you can always realize that the left side of the equation refers to the incident side. So you could do ni sine theta I. And the right side of the equation refers to the refracted side. So you could do n sub r sine theta sub r. And you could note it that way up here too. That will make it simpler for you to manipulate those variables. Okay, let's do problem B now. Solve for the index refraction in crown glass for blue light if the angle of refraction is 23.71. So this is the same exact problem, but with a new angle of refraction. We're going from air to crown glass. You're going to write down your knowns and your unknowns, and you're going to write down Snell's law. You're going to solve Snell's law for the n of crown glass, and then you're going to substitute in. And what answer did you get? Well, hopefully you got 1.531. And if we now go back and look, 1.522 and 1.531, 1.522 fits in here and 1.531 fits in here. So you can see that they slowly increase in this table. Okay, Let's finish the problem now. Here we go. So now we have C, using two different colors of pencils or pens, draw the situation for A and B, for problems A and B. So first thing we need to do is draw axes and incident light, and then we're going to draw the orange ray and the blue ray, and now we have done that. Now, problem D, what is the angle between the two refracted rays? So go ahead and calculate it. Well, hopefully you realize that you could just subtract these things. You could take 23.86, subtract 23.71, and you get 0.15 degrees. And now problem E, did the light bend towards the normal or away from the normal? Well, how are you going to figure this one out? Well, look, the angle of incidence is right here. It's big. The angle of refraction for each of these is right here. It's smaller. So this bent towards the normal, right? And finally, which color bent more from its original path? Why don't you go ahead and write down your answer? Okay, the original path would have taken it this way, right? Like this. So orange bent away from the original path, but blue bent away more. Okay, that's it for today. Hopefully you have some questions that you're going to bring to class. And until then, think hard about physics, and we'll see you next time.